Imagine your API server just went viral. 1,000 concurrent users hit a page that requires a specific database query at the same moment. What happens?
Without any optimization, your server fires 1,000 identical database queries. Each one goes to the database, waits for the result, gets back the same data, and returns it to its caller. You've just hammered your database with 1,000 simultaneous queries for the exact same piece of data.
The database saturates. Latency spikes. Your app slows to a crawl.
This is sometimes called the thundering herd problem, many callers stampeding toward the same resource simultaneously. The solution the book presents is request batching. And the core insight is deceptively simple: if multiple requests arrive asking for the same thing before the first one has returned, don't execute them separately. Execute exactly one actual request, and share the result with all callers.
Here's how it works in practice. You maintain a map, call it pending requests. The keys are the request parameters, the query, or a cache key. When a request comes in, you first check if that key is already in pending requests. If it is, meaning an identical request is already in flight, you don't fire another request. Instead, you attach the caller's resolve and reject functions to the existing in-flight request. When the original request completes, you resolve all waiting callers with the same result. If the key is not in pending requests, this is the first request for this data. You fire the real request, store a list of waiting callers under that key, and when it resolves, you call all of them. The result: one database query satisfies 1,000 callers. That's not a 2 times improvement, it's a 1,000 times reduction in database load.
The math is genuinely shocking when you think about it at production scale.
After you've seen request batching, the next optimization layer is caching.
And there's a subtle but critical implementation detail that most developers get wrong the first time.
The naive approach to caching: when a request completes, store the result value in a cache map keyed by the request parameters. Future requests check the cache first, find the value, and return it without hitting the database. This works. But there's a race condition.
Consider 1,000 concurrent requests arriving simultaneously for the same uncached data.
The first request fires.
Before it returns, 999 other requests arrive, check the cache, find nothing, and each fire their own database query.
The cache is empty because the first request hasn't resolved yet. You're back to the thundering herd problem for that first request wave. The fix is elegant: cache the promise itself, not the resolved value.
When the first request for a given key arrives, you create the promise for the actual fetch, immediately put that promise object into the cache under the key, and return it. Now, before the promise has even resolved, the next 999 requests arrive, check the cache, find the promise object already there, and attach a .then handler to the same promise.
All 1,000 callers are waiting on one promise. One database query satisfies all of them.
When the promise resolves, all the attached .then handlers fire simultaneously with the same value. Cache hit for every subsequent request, even those that arrived while the first request was still in flight.
This is a technique sometimes called deduplication of in-flight requests, or request coalescing. It's built into React Query and SWR, 2 of the most popular data fetching libraries in the React ecosystem. You're looking at the core of how they handle simultaneous fetches for the same data. Let's make this concrete with the implementation structure the book describes, because the code reveals something important about how these two techniques compose. Start with your cache, a plain map where keys are serialized request identifiers and values are promises. When a request comes in, serialize its parameters to a key. Check the cache. If the key exists, return the cached promise, done. One line. If the key doesn't exist, this is a cache miss. Create the promise for the actual database call. Store it in the cache under the key immediately, before any await, before the request completes. Then return that promise. Now, when does the cache expire?
The book walks through several strategies. The simplest is a time-based expiration: after n milliseconds, delete the key from the cache so future requests fetch fresh data.
You set up a set timeout when you insert the value.
Depending on your data's volatility, this might be 100 milliseconds for highly dynamic data or 60 seconds for relatively static data.
There's also error handling to consider.
If the request fails, you should remove the key from the cache immediately. You don't want a cache rejection and permanently block callers from getting a result.
The cleanup happens in the .catch handler of the request promise.
The book also warns about cache invalidation being famously the second hardest problem in computer science, the first being naming things.
A time-based expiration is simple but imprecise.
Event-based invalidation, where you invalidate the cache entry when the underlying data changes, is more precise but requires knowing when changes occur. Depending on your consistency requirements, you might use one, the other, or a combination. The composed system, promise-level caching plus batching, means that under any load pattern, you execute at most one database query per unique data key per cache TTL period.
That's the performance ceiling you're aiming for.
Let's zoom out from the implementation and look at where these patterns appear in production systems you already use, because the impact is significant enough that major infrastructure has been built around these ideas. Data Loader is a library from the Facebook engineering team, originally built for GraphQL servers. Its entire purpose is batching and caching for data fetching. It works like this: instead of calling the database directly in every resolver function, you call dataloader.load key. Dataloader batches all the load calls that happen in the same tick of the event loop into a single batch function call, one database query for all keys requested in that tick. And it caches results so the same key isn't fetched twice within a request.
In a GraphQL server, this is transformational.
Without Data Loader, resolving a list of 20 posts where each post needs its author's data might fire 20 separate queries to the users table. With Data Loader, all 20 user IDs are batched into a single query. Select asterisk from users where IDIN 1, 2, 3, 20.
One query replaces 20. This is the n+1 query problem solved automatically. React Query and SWR implement the promise-level caching pattern we described.
When two components on the same page both request the same data, the library deduplicates them automatically. One network request, both components receive the same data.
This works even across component unmounts and remounts. Redis itself is often used as the second level of caching in these architectures. Local in-memory cache for the current Node.js process. Redis for shared cache across multiple instances.
Understanding how to compose these layers, in-memory batching, in-memory caching, shared Redis cache, is what separates systems that scale gracefully from systems that buckle under load.